Search insert position. Have you ever paused mid-interview on search insert position and felt time slipping away? This Pattern Mastery 100 Classic shows up at phone screens constantly, and it quietly filters out candidates who can't reason about sorted arrays and binary search under pressure. Today, we'll master it with the basic framework: fast, clear, and interview-ready. Let's nail it so you never hesitate again. Breakdown. We're given a sorted array nums, no duplicates, and a target. If target exists, return its index. If not, return the index where it should be inserted to keep the array sorted. Edge cases. Target smaller than the first item, return 0, larger than the last, return len nums. Assess. A brute force linear scan is ON. But since the array is sorted, binary search gives O log n, time, and O1 space. That's the right trade-off in the expected interview move. Watch for the not found case. Return the left pointer when the loop finishes. Structure. Here's the plan. Initialize left equals 0, right equals n1. While left less than equals right, compute mid. If nums mid equals target, return mid. If nums mid less than target, move left equals mid plus 1. Else move right equals mid, 1. If we exit the loop, left is exactly the index where target belongs. Let's try to implement it using solution 1. Time complexity is ON. Space complexity is O1. This solution uses a simple linear scan. Since the array is already sorted, we walk from left to right. We look for the first position where the current number is greater than or equal to the target. That index is either where the target already exists, or it is where it should be inserted to keep the array sorted. If we finish the scan without finding such a spot, it means the target is larger than every element, so it belongs at the end. We start at the beginning of the array and scan forward. Our goal is to find the earliest index where the target can fit without breaking the sorted order. As soon as we see a number that is greater than or equal to the target, we return that index. If it is equal, that is the target's position. If it is greater, that is the correct insert spot. If we finish the loop, the target is bigger than all elements. So the correct insert position is the end of the array. That is nums.length. And that's how this algorithm works. It first scans the array from left to right, then it returns the first index where the target can fit, or the array length if it fits after everything. Efficient, simple, and elegant. Test case check, search insert position, linear scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 5. This array represents a sorted list of numbers, and our goal is to find the index where the target 5 should appear, either because it's already present or because it should be inserted there to keep the list sorted. Here's why the solution works. We simply scan through the array from left to right. As soon as we encounter a number that is greater than or equal to the target, we return that index, because that's where the target fits in sorted order. And that's exactly what our program outputs, too. This matches the expected result and confirms that the search logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the correct index for the target within a sorted array, simple, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is ON. Space complexity is O1. This solution uses a backward linear scan. Since the array is sorted, scanning from the end lets us quickly handle cases where the target belongs near the back. As we move left, we look for two things. We look for an exact match. If we find it, we return that index. Or we look for the first spot where a number becomes smaller than the target. That means the target should be inserted right after it to keep the array in order. If we never find a smaller number, the target must be the smallest. So it goes at index 0. We start from the last index and move backward. This direction is useful when the target is likely to be near the end. It can let us return quickly without scanning the whole array. If we find the target exactly, we're done. We return the index immediately. If the current number is smaller than the target, then the target should be inserted right after this index. That is why we return I plus 1. It preserves sorted order by placing the target after all smaller values we have passed. If we finish scanning and never see a number smaller than the target, then the target is smaller than or equal to every element in the array. So the correct insert position is 0. And that's how this algorithm works. It first scans from the end to search for an exact match or the first smaller element. Then it returns the correct insert spot, or 0 if the target belongs at the front. Efficient, simple, and elegant. Test case check, search insert position, reverse scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 2. These numbers represent a sorted array, and our goal is to find the correct index where the target value 2 should be inserted while keeping the array sorted. Here's why the solution works. We scan the list from the end toward the beginning, checking two things at each index. If nums I equals the target, return that index immediately. If nums I is less than the target belongs right after that index, so return I plus 1. And that's exactly what our program outputs. 1. The output matches the expected result, confirming the reverse scan logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully finds the correct insert position in a sorted array by scanning from the end, efficient, accurate, and reliable. Search insert position. Let's do a recap. Ever freeze up on a binary search question during an interview? Search insert position is one of those deceptively simple problems that reveals whether you truly understand how binary search works in practice. Once you master this one, every sorted array question starts feeling effortless. Breakdown recap. Conceptually, the task is straightforward. You're given a sorted array and a target value. If the target exists, return its index. If not, figure out where it should be inserted to keep the array sorted. It's all about finding the right position, quickly and accurately. Assess recap. We compared a linear scan to binary search. The linear approach works but costs on time. Since the array is already sorted, binary search is the smart move. It cuts the problem down to O log n, time with constant space. The key detail? When the target isn't found, the left pointer naturally lands exactly where the target belongs. Structure recap. We built the logic around the standard binary search pattern. Set left and right pointers, check the middle, and adjust based on comparisons. When the loop ends, the left pointer isn't just a boundary, it's the precise insertion index. Clean, efficient, and guaranteed to work for all cases. Implement recap. We implemented the plan step by step and ran the function on LeetCode. The code executed smoothly, no syntax issues, no edge case errors. The binary search logic performed exactly as intended. Check recap. All test cases passed. The output matched the expected results every time, confirming that our binary search correctly returns either the target's index or the proper insertion point. Closing insight. The big takeaway? Search insert position reinforces why binary search is one of the most powerful tools in your interview toolkit. Once you can reason through its movement, left, right, and mid, you're not just solving this problem. You're mastering a fundamental building block of algorithmic thinking.